So I'm at Quantinuum. I mean, I assume not everybody's has a quantum computing background. Maybe you do. But we're a company of around like 600 people now, and we kind of like spun out from Honeywell, which is more known for like air conditioners and things, but they actually do a lot more than that. Um, and also a merger with Cambridge Quantum. So we basically have half our people kind of over in the US side and half in the UK, but we also have offices in Germany and Japan as well. And we do ion trap quantum computing. So I thought, given this conference, it makes sense to kind of, since it's all about like bridging the gap between NISQ and early fault tolerance, that would make sense to kind of do a review of sort of the buildup of QEC that we've been doing, experimental QEC we've been doing at Quantinuum. So, okay. I think also I probably have more slides than I should, like 30-ish. So I'll try to keep everything high level and adapt as appropriate. But to give you kind of an idea, the first device that we kind of released commercially was this kind of linear trap. So not all ion trap computers are the same. They're built on slightly different technology. So kind of the early day ion traps kind of had all these ions in a kind of a giant chain. They can kind of imagine kind of oscillating together. And you had all-to-all connectivity by kind of doing this single addressing with different lasers on the ions. But you kind of had less and less confinement as you kind of went out in the chain, as well as kind of the light can potentially bleed over onto other ions and so it gives you like kind of bad crosstalk for like 2-qubit gates and things. So the QCCD architecture kind of like solves this by effectively having a bunch of mini ion traps inside of a larger ion trap. Essentially, we have little small crystals. So either we always have like a qubit ion and a coolant ion. And we might either have a pair of 4 ions, which would have 2 qubits in it, or a pair of 2 ions, which has a single qubit in it. And so we kind of merge and split these ions and then move them to the gate zones. So that allows us to have a lot of control and keep everything separated, and so we don't have all this crosstalk and things. And it's actually very easy to kind of noise model because everything's nice and separable.
And this crosstalk effect doesn't really happen that much, even when you have 2 of these qubit ions together, like very, very close? Or?
Yeah. Well, we bring the two together and merge them into a single crystal in order to do a 2-qubit interaction.
There we go.
Yeah,
okay.
But the other ions are not merged in with that. Yeah.
So you have like a storage state and an entangled like state, basically.
Yeah. Okay. Yeah. Essentially, over in the schematic, sorry if you're colorblind, I don't know how this renders, but these arrows kind of indicate the lasers, and kind of those blue regions where the lasers are going through are kind of the gate zones, but we can move them out to the side to the other regions. And initially we started out with 10 qubits, but then we upgraded that trap to 20 qubits, and the experimentalists are constantly upgrading the devices. So it's not like we just fab one thing and it remains how it is. It's constantly improving. And then we moved to this H2 device, which is kind of a racetrack. So it's like quasi 2D, which you can kind of see the ions kind of zipping around. You can actually fluoresce them and see the ions. It might be hard to see, maybe if you squint. And let's see. This is kind of a very toy schematic of kind of these first ion traps we had. So if you imagine you have a QCC architecture with just 3 ions in it, this kind of darker region over on the side represents the gate zones. So we have our first 2 qubits that we want to apply the single qubit gate to, I guess we always initialize in the all 0 state, so lasers go off and do that. I'm also a QEC theorist, so I'm not an experimentalist, so they're all just lasers going off. I don't know what the actual interactions are. Anyway, and if you want to do the Hadamard, they're already kind of pre-sorted into those zones, and so we can fire the lasers, they apply the Hadamard. Then we need to do this 2-qubit interaction, so we need to bring the red and green qubits together and join them into a single crystal. So they come together, merge, and then lasers go off to a 2-qubit gate, Mollman-Sorensen gate. And then to do this other 2-qubit gate, we have to, between the red and blue qubits, we have to kind of flip that around and then split and join. So you'll see that. So we join them into and move them over to the other gate zone. Lasers go off and apply the 2-qubit gate. And then if we want to do a measurement, then we usually isolate that qubit into the zone. Yeah.
Sorry, is swap a gate?
So swap is a physical operation. So what's kind of interesting about the ions is that we have this overall charge that we can kind of grab onto and move the ions with, but that's not directly coupled to the actual qubit information. So they're in a separate energy level. So even though we're moving around, it doesn't disturb the qubits. The part where transport does slightly affect things is that we have, whenever we're merging these 2 qubits together, the 2-qubit gate is through this Mollman-Sorensen action, which is kind of has to deal with motional modes and stuff. So we have to cool it down and so yeah, we do that before each 2-qubit gate so that we have So that's the one place that it can affect things.
What is actually taking the time here between each of these operations? Because I see in the final section you have the 2-qubit gate taking up an entire time step, right? But in all the other ones, there is a move operation that is taking place in each time step as well as one of these gates. So which one is taking up a total time?
So the transport does take time, and also cooling the gates for doing the 2-qubit gate takes a decent amount of time too. It's all relatively fast. I kind of forget the time scales now, but I would say half the time is in transport and half the time is in cooling for the 2-qubit gate, and the actual gates themselves are really fast. They're super fast.
Okay, so you assume a movement and a 2-qubit gate both take about the same time, approximately?
Yeah.
So should you have more time steps here?
The transport actually is typically, I think, a lot faster. I guess each step is really fast, but you might have a bunch of combined steps. And also, you have typically have multiple gate zones, so you're doing these things in parallel. So it's not all serial. Yeah.
Interesting. Okay, thank you.
So your swap operation is done purely electrostatically? Like you move them around?
Mm-hmm.
Okay.
Yeah, it moves in 2D space, or 3D space. Yeah.
I'm sorry, I don't mean to ask too many questions right ahead, but do they have to be in this 2-ion entangling state that you're talking about in order to swap, or can you swap them even when they're alone?
I mean, if an ion's all, maybe I don't understand. If an ion's all by, maybe whether you have to merge them into a crystal in order to do the swap.
That's what I'm asking. Yes.
I'm not sure. I mean, they probably have to get. I don't know the details of exactly whether they're truly in a crystal or not.
Sorry, I don't want to derail us too much.
Yeah, I guess just merging into a crystal operationally is do you need also laser, or what kind of?
No, it's all through electrodes and things, and you basically have these wells that you have this rotating electromagnetic field that you're kind of it's mostly, I think, that you're creating wells with, and so it's just merging the wells together basically, and then unmerging it.
So it's the same as just moving.
Yeah. Okay. Let's see. And then in this picture, I guess we're getting to the measurement. The qubit happens to be all by itself, this green one. Oh, I guess I ran past that. Anyway, you imagine laser go off. Okay, there we go. I did it. Laser goes off, and you can do the measurement there, and you can continue on. So it was we were able to do mid-circuit measurements relatively easy early on, because just the way we can separate things. There's a little bit of crosstalk due to photon scattering and stuff, but we're kind of that's relatively low. It's maybe 10 to the minus 6 or something, or maybe lower error rate, and it is effectively like the environment sort of measuring other qubits, but you can think of it as just adding to the depolarizing channel. So it's like single qubit crosstalk, so it's not, yeah. Anyway, We've just released this Helios device, which has 98 qubits. It has experimentalists like to talk in things in terms of fidelities, which is probably going to get more and more awkward as we reduce those, especially on the logical level. So I probably should have written this for a QEC audience where we talk about error rates. But yeah, really low single qubit or really high single qubit fidelities, really high 2-qubit fidelities. We can keep on pushing that down. The plans is probably to get around 10 to the minus 5 error rate for 2-qubit gates. And then we have this thing, previous devices would have to take in a program and kind of statically compile that and work out all the transport operations and the native gates and whatnot. Now we have a real-time engine that takes in the operations and works out the transport on the fly. That means that you can have very generic programs that have loops and branches and all sorts of stuff. So we're no longer stuck with like static chasm circuits.
The swap that you showed, is that operation of comparable 2-qubit fidelity?
No, it's the way the swap. The way I do a lot of the error modeling, and the way we model that is that the ions are slightly affected by the magnetic field of the environment, very slightly, and so it's just about the time duration. It applies a slight coherent rotation about the z-axis, so it doesn't really I wouldn't really think about it being part of the gate. I guess you could imagine kind of wrapping that in that, but it's more easier to think about the time it takes to do transport or other things. I
think there's a misunderstanding happening, and I think it's happened 3 or 4 times. Just to be clear, when you say swap, with respect to moving
physical swap,
that is not a swap operation. It's not a 2-qubit gate, right?
It's logically equivalent. I think so, yeah, but it's not. You're not using a unitary to do it. You're physically swapping it. Yeah. But I think it's logical. The information, the operation is logically equivalent whether you do a physical or unitary swap.
But it's not a physical swap gate.
It's a physical move qubits. Yeah, it's physically moving the qubits around.
What's the difference?
Yeah, what's it?
But you end up with the qubits that were here and here, here and here.
Yeah.
But you don't use a laser for it?
Yeah, no laser for that. You're physically moving the qubits around in the trap.
So it is a physical 2-qubit gate with a fidelity, and that's the fidelity?
No, this is the fidelity of unitaries. And what I was saying is that when it comes to transport, which swapping is included as part of the transport, you're moving things around. That the way that it's better to think about is the amount of time that takes to do transports or gating. You have this very slow coherent Z rotation. It's very small, but it's there. But we don't typically think about packing that into the 2-qubit gate in kind of a gate model-y way.
I apologize if you already said this, but the measurement error rate?
The measurement error rate is roughly around the 2-qubit gate error rate as well. I don't, at least that's for H1 and H2, they switched ions, so I don't, it's probably the same, or it might be lower now. I don't remember, I think we now use barium, and before we were using ytterbium, such and such an ion, I don't remember the numbers. I think the measurements are actually a lot lower, but I don't know. I think prep has always been really low, 10 to the minus 6, and so is all for spam is all on kind of the measurement side of stuff.
So when you measure, do you lose the ion or do you keep
No,
it?
keep it. Yeah. All right, and because of this real-time engine stuff, we now have this kind of the software engineers over at Quantinuum kind of geeked out, and they created this general-purpose programming language. I guess I actually have a little intro slide to that, but before that, even from the beginning, we were doing real-time decoding. First, we did lookup tables, and we've eventually we use this thing called WASM, WebAssembly, to be able to allow users to write whatever decoder they want and kind of run on a hybrid compute chip that's a CPU. And now we've integrated a NVIDIA Grace Hopper box as well. So you can potentially run in real-time decoders that use GPUs. So you can do either CPU or GPU real-time decoding. So this Guppy stuff, it basically is a language embedded in Python that looks like Python. And this is kind of showing off like repeat until success, for example. You have your Hadamard's, Toffoli gate, and so on, and it's kind of showing like doing a for loop, doing it, ifing on the measurement results, and keeping track of it. Actually prints out to the user like those statements. And so you can, in general, write all sorts of crazy programs if you want. And so we're no longer stuck with like static, classical quantum circuits. All right, I kind of went a lot forward in time, but I'm going to step a little bit back with the QEC experiments. We're already 16 minutes in. So the first experiment that we did, we started with H1-1. We have great naming conventions, just a letter and a couple of numbers. It originally had 10 qubits in it, so that allowed us, to do like the Steen code, which has 7 data qubits, and then we can introduce 3 ancilla qubits. And you use the scheme by Reichardt, which is over on this side. This is like a QEC gadget. So you're measuring syndromes where the color. So this is a member of a color code, and they have hook errors. And Reichardt figured out how to kind of basically measure both syndrome and flag information at the same time. But then you don't really know whether you have a syndrome or a flag bit at that time. So you have to do this conditional operation. And so effectively, if you see a change in this flagzilla information, then you have to run another round of syndrome extraction to kind of distinguish whether you have what exactly happened, whether it was a hook error or whether it was a normal sort of qubit error. And so even from the beginning, we're kind of doing conditional operations where we only measure, we measure up to 2 rounds of syndrome extraction per QEC gadget. That's enough to be fault tolerant to qubit and measurement errors. So by doing this conditional thing, you don't have to do 3 rounds, for example, which is more traditional. And on average, actually, you're like 80% of the time at the error rates at this time, we're only doing 1 round per gadget. So you're not. So it's I think 20% of the time you actually ran all 3. So it might be like 1.2 rounds or something like that is actually what you end up doing per step. And so these are the results. We looked at the X, Y, and Z basis. And at this time, no one was people were pretty much just encoding and then decoding the code experimentally. And so this is the first time that you're doing multiple rounds of syndrome extraction for a full QEC code. I think previously there was some work on repetition codes doing multiple rounds, but for an actual QEC code, I believe this is the first. And we're using lookup tables in order to decode all this in real time. Yeah.
And the y-sociological error rate, is that a rate per cycle?
Yeah, I think the next slide might have a better breakdown. So yeah, we extracted the effect by matching these curves. We extracted we're having fidelity. So 1 minus this would be basically the error rate, the fidelity per cycle, and the fidelity for the logical span. And so we're kind of, the per cycle thing is a bit higher than like the 2-qubit gate. The span is around the physical 2-qubit gate error rate at that time. You can see that kind of the physical spam was slightly worse. And then we also have simulations where we didn't really know how QEC should perform on the device. So I took all the work that I've been doing in grad school, doing error modeling in QEC, and then built a detailed noise model that's more than just depolarizing noise. It had leakage and potentially coherent noise approximations and other stuff. And we're able to kind of better understand what was happening in the device. So the dotted lines are the simulation. And we're also, like, I took the output of the compiler that actually gets sent to the device, and it's running those actual like transport operations and native gates in the simulation. But yeah, those are the numbers at the time, and this is like 5 years ago or something like that.
Yeah. And so just to be clear, this is, to me at least, a picture of a code operating above threshold, right?
Yes.
So this is the before picture, and you're going to show us an after picture in a second.
Maybe. I mean,
Okay.
they get better and better.
Okay.
Yeah. All right. Then the next year, we got upgraded to 12 qubits, which allowed us to, we wanted to do a 2-qubit gate. And constrained to that, we could do peaceable fault tolerance, which is a cool thing that I think Yoder and others figured out. Essentially, it's like if you have an operation that isn't fault tolerant, you can potentially like break it up into pieces where you then run cinder extraction on those pieces and are able to put that information together and make it fault tolerant. So you kind of capture the error before it spreads badly through the circuit and allows you to remain fault tolerant. So for 2 copies of the 5-qubit code, we did this peaceable fault tolerant gate. It didn't perform great. Like this is kind of, there's a lot here, but essentially we're starting with spam and then we're applying C0 without any of the cinder extraction, and eventually we get down to applying the full cinder extraction fault tolerantly and things. So you can see, and this is just plotting the number of physical 2-qubit gates it takes to do these different circuits. So we're around like 70% fidelity for the X and Z basis, and around, I guess, 50% fidelity for the Bell state, which I think completely random is 25%, something or other. But it is a more complicated circuit than what you'd want to do with like the color-coded surface code, which while we were doing the experiments and writing things up, they upgraded yet again, annoyingly but also awesomely, to 20 qubits, which was exactly the number of qubits that we needed to do 2 copies of the Stein code and to do a transversal gate. So it's a much simpler circuit. And then we followed it up with potentially cinder extraction or QEC cycles after that, which we didn't really need because we have a measure out phase, which makes this completely fault tolerant. So you can kind of drop the QEC cycles, but kind of just wanted to evaluate what that looked like. And then you get like this horsey figure, constellation thing. But so just the fault tolerant QEC without the extra QEC cycles was around this. So that's 97 to 99% fidelity. X-base is a little worse because we have this memory error thing. So it's that slight rotation around the Z-axis, which shows up at the logical level as well as Z error. So you get more logical Z errors. But yeah.
Sorry, I think I'm having trouble
Yeah, this might be too much
parsing
information.
these plots. Yeah, could you just say maybe what the horizontal axis responds to and what the takeaway is?
So this is a series of experiments that maybe shouldn't be shown in the same plot, but it kind of like gives you an impression of, okay, with more complexity. So this is more, how many physical gates does it take to do? What is the fidelity of those different experiments?
Should we think of those as like different possible syndrome extraction circuits?
So, well, so over here, we're starting with spam. So we don't have any 2-qubit gates or QEC, except for like the measure out stage, which also, measures syndromes effectively by measuring out the data qubits. You can then work out the syndromes and apply decoding to that and correction. So I think spam 1 is when you ignore the correction. Spam 2, it's very hard to read. I'm sorry. I probably shouldn't have put it for this talk. Spam 2 is when you actually apply the fault-tolerant correction, or when you do things fault-tolerant, you actually apply the correction, so you see the fidelity goes up. Then we just include the transversal C0, which is fault-tolerant because we have this QEC, the measuring out things provides a correction. And so we're up here. But then when we start to apply a little bit more cinder extraction, it's over here. And finally, we have the CNOT with the full cinder extraction, or extra QEC rounds over here. And kind of like Michael was saying, like using QEC is a great analogy that he gave, is you're fighting fire with a fire extinguisher that's on fire. That was awesome. If you don't mind, I'll try to, I might steal that. Okay. But yeah, every time, like people sometimes have this naive picture that whenever you apply QEC, it somehow like gets rid of errors. All it does is it slows down the increase of errors. So like entropy always increases, everything gets worse, unfortunately. But the job is to just slow down the process of it getting worse. So, yeah. So yeah, we're just slowing it down so we can do more and more gates. But it's always, no matter what what you do, even QEC is going to reduce the fidelity. So, but luckily it actually didn't like completely drop it. It was somewhat plateaued. Yeah.
Yeah, this is super interesting that it's like plateauing, but I assume that right after this, that's like going to drop precipitously, right?
If you keep on applying QEC over and over again, it'll drop.
And what's also kind of interesting here is that at least what I'm seeing is a biased noise model, right? Like you seem to be more biased towards Z errors, right?
Yeah.
Nice.
Yeah.
Okay.
It's because
do you incorporate that into your error correcting codes?
Yeah, and we saw that in
Awesome.
the simulation, yeah, it's that memory error that's applying the small coherent Z noise that's the bias. Everything else is not exactly, but closer to equal probability of polys.
Sweet. Looking forward to the schemes that take care of that.
All right, and then, so yeah, whenever you just look at not applying the extra QEC cycle afterwards, then we actually have basically the logical CNOT performing better than the physical CNOT. However, of course, like really, like I don't think looking at component level performance of different QEC operations is really quite right, because whenever you start putting these things together, the context of how the experiment actually works changes things, and so the error rate might be different whenever you actually start doing an algorithm. So I think we've been really focused on how well memory performs, which is really important. That takes up a lot of the error, but it also thinking a bit about like how these things all combine and how it actually affects the overall algorithm is probably, I think, more of the right approach to evaluate how QEC performs. So this is a little bit. So I'm just pointing out I'm kind of a little bit cheating here, but is also hinting at we're starting to do better at the logical level compared to the physical level for certain components. And then after that, in 2004, a colleague who does tomography and doesn't really do QEC took some of the code that we wrote, kind of made something that makes it easier to write logical experiments, and then started doing logical tomography. So he did like logical two-qubit RB, and was able to calculate that the logical two-qubit gate error rate or fidelity was around here, so a decent number of 9s. Then he did logical
Wait, sorry, can you go back one slide? It seems that the average fidelity went down between H1 and H2. Is that correct?
Yeah, it looks like that. It might be kind of close together within error bars, because if you like subtract the 2 and add the 8, be almost the same. But it could be due to like maybe the transport was more complex because now you have more qubits. I don't really know, but they look like they're like I think these are 1 sigma error bars too, so they're probably like statistically equivalent. Then he did logical T benchmarking. So essentially, he was trying these 2 gadgets. These are non-fault tolerant, so he didn't, I believe. But he was trying out these 2 different methods. One method is the different ways that you inject a T gate. You like prepare a resource state, and then you measure out one of the qubits, and then it applies it to the logical qubit. And there's 2 different ways that you can do it. One kind of teleports the information. What he found was the teleporting version performed better, which you can imagine maybe it's like getting rid of leakage errors, or maybe the increase in coherence. So it'd be interesting to kind of revisit that. And then he did logical QFT. So he put together all the components. I think for the control T gate, he did some weird, some recursive teleportation of the T gate. But he got pretty high results, like around 80% fidelity for the different computational basis states for doing QFT, which I think random might be 25%. I don't really remember. All right, moving forward.
Excuse me, just one question.
Yeah.
Is that still Steam code?
It's still the Steam code, yeah. So we've been doing a lot of Steam code, but then we've been branching out a lot recently. So, okay. With Microsoft, we looked at both the Carbon code and the Steam code again. This time we're preparing a logical Bell resource state that is useful for logical teleportation, for example. We're able to push down the error rates a lot. Moving ahead. So we did, with the Steam code, yet again, we did different versions of teleportation. One is using the transversal gate, and we either applied or not applied an extra round of QEC. Don't really need to do that. One thing that's cool about teleportation is it effectively a different way to do QEC. It's known as Keneal-style cinder extraction, where you're both teleporting the information, but you're measuring off in the X and Z basis some of the original qubits, and that propagates X and Z errors to those two different branches, and allows you to effectively get single-shot error correction while teleporting your qubit over to a different logical qubit. And it also allows you to turn non-qubit errors into qubit errors. So, for example, leakage just doesn't apply one of the physical 2-qubit gates whenever the qubit's leaked. So it just kind of depolarizes one of the qubits. Which is kind of cool, but potentially you can also herald it. Think about heralding that as well. So this is also a way that maybe we can trade space for time. So it allows you to quickly do QEC, but you have to create these extra Bell resource states to do that. Okay, so we did the transversal version, and then we did a lattice surgery version. And back in the day with Andrew Landahl, as a young grad student, I think it was the second paper on lattice surgery, back when we didn't really understand lattice surgery, kind of worked out how to do that for the color code, so I was able to reenact that experimentally. It didn't perform as well, so over on the left-hand side, you have the physical qubit version of the teleportation, basically the Keneal-style transversal gate version with the 0 QEC, the extra QEC just for fun, and then XXMZZ is the lattice surgery version. We're kind of merging and splitting these codes together, doing joint operations between the codes to kind of measure joint checks between them, and then not measuring it, and so on. And then 1-bit teleportation, where you kind of can take this circuit and kind of show that it's equivalent to, of course, 1-bit teleportation. Lattice surgery has the advantage that sometimes there's hidden parity checks that you can just get rid of and just do through the operation instead. Yeah.
So what this graph appears to be saying is that this teleportation style lattice surgery seems to be the most effective for infidelity. But that's what he's aiming for, right?
Yeah, it effectively gave us the same. For the Keneal-style /0 QEC thing, it gave us the same fidelity as doing on the physical level. And then, a year later, because they keep on improving things, I reran the experiment, and now it's much better. So this is the original plot if we're just looking at the Keneal-style versus physical. And now the new Keneal-style versus physical, it pushed things down. And now before, it was within error bars the same. Now the logical version is 2 times better. So now we're doing much better, and probably if I reran it now, it'd be even better. They keep on just squashing the memory error and the 2-qubit gate error over and over again. So this kind of shows even in the same device, we are making improvements, and yeah. And I don't have very much time. But
You say same device, you mean literally it's the
it's
same.
the same device.
It's the
yeah.
same one. You're just
This-
fiddling with the
This is
numbers.
the exact same device, old new paper. This is a sister device that's the same architecture, but these two are practically the same as each other. Okay, and since maybe this is good to start wrapping up, we've now moved beyond doing just the Steam code, and we've done, I think I've counted maybe 13 different separate codes. They include stuff like the 4-dimensional surface code, these weird symplectic double codes where you're kind of twisting things around, concatenated codes, Reed-Muller codes, and different LDPC codes and stuff. So the device is really flexible, so we can try out all sorts of different possible codes and see which one makes the most sense for our technology. And so, yeah, you can visit all those different papers. Yeah, and so one of the errors that keep on being mentioned is this memory error. A colleague of mine looked at decoherence-free subspaces and concatenating that with like the 5-qubit perfect code, and we see that we can really kill off a lot of that memory error. So the red line is physical error, and this is fidelity, so down is bad. Just the decoherence-free subspace code is this green line, so it's able to preserve fidelity a lot more. And then this concatenated code is the blue line, and so concatenating a normal QEC code with this decoherence-free subspace code, which is a 211 code, so it's not a proper QEC code, we can see that we're able to protect the fidelity a lot more. So we can potentially concatenate it, but also for a lot of this stuff, we're not doing DD, we're not doing polytwirling, which we should be doing, but yet we get all these fidelities. So we probably should be more aggressively applying other tricks in order to push down the memory error. I just like making it more challenging for experimentalists, so they'll push down the base error, and yeah. Anyway. And then we've done a variety of ways to prepare magic states, which is required for universal computation. So, for example, a collaborator with Isaac Kim's group and Sandia did this, created a 3D color code, which has a transversal T-gate, and then did a one-way teleportation of that to a Steam code. But we also have methods where one of my colleagues at Quantinuum was able to do a 622 code that prepared a magic state that has a fidelity of 7 to E minus 5, and then doing simulations of concatenating that for a 344 code. The simulations seem to indicate that we can get magic states the 6 e to the minus 10, and you can imagine teleporting that over to a different code. So we have many routes to potentially do magic states, and there's other non-Clifford gate stuff. And then I don't have very much time, but this actually might be more interesting to people. We did the error detecting code and did phase estimation and got relatively close to the actual known value for the hydrogen molecule. Then we took QEC, the Steam code yet again, and we did partial fault tolerance. So fault tolerance itself is very expensive because of all the gating that you have to do. And we were able to get the actual value within 0.01 Hartree, which I'm told is somewhat chemically relevant. So you can start saying things, even though this is well known a thing. It just kind of it's a proof of principle that we can start doing on the logical level these sort of experiments, and then we'll keep on pushing on it. And then future devices, we're going towards grid traps. Here's a picture of a grid trap in a test stand moving around, and it doesn't really heat up anything, so there's low error rates to have these grid traps. Roadmap, every company needs a roadmap, apparently. But yeah, we're going from this Helios device, and the next devices will be grid traps, which will make sorting and transport a lot faster, and we have other tricks to make gating even faster. So cool.